everyone, today we start Chomsky hierarchy. What is Chomsky hierarchy? This is the classification of the grammar. You can say here type 0, type 1, type 2, type 3. This Chomsky hierarchy classified the grammar. Then first one grammar is the type 0 is the unrestricted grammar, type 1 is the context sensitive grammar, type 2 is context free grammar, type 3 is regular grammar, and each grammar generate a language which is also accepted by a finite automata. Like type 0 grammar, it is an unrestricted grammar which generate recursive enumerable language then accepted by the Turing machine. Like type 1, it is a context sensitive grammar and generate context sensitive language then accepted by the linear bound automata. Like type 2, it is a context free grammar then generate context free language accepted by the push down automata. And type 3 is a regular grammar which generate regular language then accepted by the finite automata. So, we know the finite automata, then after that we will go to the push down automata and see here this is the type 0, type 1, type 2, type 3, this is the Venn diagram. In this Venn diagram what we get here, if any regular language is there, that is accepted by the finite automata, also it is accepted by the push down automata, also it is accepted by the linear bound automata, and also it is accepted by the Turing machine. This is the higher machine of the theory of automata. And see here one language, if regular language is given, suppose one regular language is given, L is a to the power n, n greater than equal to 0. For this language we can design as a finite automata, also we can have design a push down automata, and also we can design in Turing machine also. See here, what is the meaning here? Type 0, if any language is in type 0 that cannot be accepted by the push down automata, cannot be accepted by the finite automata. See here one example. This regular language, you know the regular language is there, for that we can have epsilon NFA, we can have DFA, we can have regular expression, also we can have right linear regular grammar, left linear regular grammar. So, we will take an example here. See here, L is a to the power n, n greater than equal to 0. Here, what are the strings are generated by this regular expression, this language? Strings are minimum epsilon, this is A, double A, triple A, then 4A, like that this will be go to infinite number of A. And for this language we can design a finite automata, also we can have design a push down automata, also we can design a Turing machine. Now, see here what are the regular expression for this? Regular expression for this is A star. You can say this A star can represent all the strings which is generated by the language. And here also we can have a DFA, deterministic finite automata, DFA already we know, and DFA we can have a DFA, that is A, this is Q0 and this is A, and this is initial state and final state. And here all the strings whatever generated by the language a to the power n, n greater than 0 also accepted by this the finite deterministic finite automata. Also for the NFA, we can design NFA for this, NFA for epsilon NFA for A star. Here we can design, this is A, this is epsilon and this is epsilon and this is epsilon and this is epsilon and this is, you can say this is the initial state Q0, then Q1, Q2 and Q3 is the final state, Q3 is the final state. here a whatever string generated by the language all will be accepted by the final this NFA. So, if any regular language is there, then we can have regular expression, we can have deterministic finite automata, we can have epsilon NFA, also we can have without epsilon NFA. So, this regular language accepted by the finite automata. Then for this also we can have push down automata, and we have also Turing machine, like all the higher machine can be accepted by the using this regular language. So, now we will go to the next context free language. Then for the context free language we can have a PDA, we can have context free grammar for this. So, we will take an example, see how this language cannot be accepted by the finite automata, then we have to go for the push down automata, we have to go for the push down automata. Suppose we will take one language a to the power n, b to the power n greater than equal to 1, n greater than equal to 1. So, what are the strings will be here? Here the strings are a b, minimum length string a b, then double a double b, so triple a triple b, then 4a 4b. If we will take here n as a 4, then 4a 4b, like that it will be continue. So, here it is equal number of a and equal number of b. So, in finite automata we do not have the memory to keep this a, you have to make it equal number of a and equal number of b. What is the finite automata? Only read the input and go ahead, but here we have to, when we will read the input we have to keep the a, and when b will come then you have to compare it. So, here we could not design in a finite. If we will take, if somebody will say that a to the power a, this will be regular expression a to the power b to the power a to the power star b star, then this is wrong. You cannot represent a star b star as a regular expression this for this language. So, here we can say this is wrong. So, this a star b star means here may be a b b one string, then a b b, then a b b b, like that string will be there. This will be any number of a, any number of b, but here we need to compare a to b. So, we need here, we cannot use the finite automata to accept this language. So, we have to go to the push down automata, where we use the stack memory, to design this push down automata, where you have to go use the, we have to take a memory it is stack memory. You have to use the stack memory to design the PDA. For this we can have a stack memory to design the PDA. So, here what you have to do, when you suppose a b b one string is there, then what you have to do, this read all the a, suppose stack data structure you have to take. Here you have to take a stack data structure like that, suppose in his bottom is z, then for all a, read all a, from the input tab you read all a, read all a, and push into all a will be pushed, then each b you have to pop 1 a, this is pop 1 a, each b you have to pop 1 a, then like that you can compare, we can compare the equal number of a and equal number of b is there, like that you have to compare equal number of a, equal number of b. If any comparison is there in language, then we could not design the finite automata, then we will go for the push down automata, we will go for the push down automata. So, now we will go to the context, another language is there, context sensitive language. See here, we have to go to the another higher machine, that is called context sensitive, language, which is accepted by the linear bound automata, So, how this is? So, here we will take one language a to the power n, b to the power n, c to the power n is greater than equal to 1. This n is greater than equal to 1. Suppose here whatever the strings are here, what strings are, if you will take n as a 1, a b c, a b b, c c, if you will n as a 2, then a b b, a b b, then triple c, like that. Here is a 2 comparison. You see here at a time 2 comparison is there, here a to the power n, b to the power n, c to the power n. Then at a time 2 comparison is there. For this we could not design the in push down automata. Definitely we will go to the higher machine like the linear bound automata, Turing machine, like this. See here, if you will compare at a time 2 comparison is there, if you will take here one stack. So, for suppose we have taken a input is a b b b b, then c c c, then what you have to do, suppose in this is the z is the stack bottom, this is the stack data structure and z is the stack bottom, then when all a you have to push a, suppose a push, then a push, then a push, then when b will become, then each b you have to pop 1 a, pop 1 a, pop 1 a, this is pop, then pop, this is pop. So, like that you have to make stack empty. So, a b is will be compared, but you could not compare the c. That is why this cannot be accepted by the push down automata. Then we have to go to the Turing machine. In Turing machine we can design this one, like you can say linear bound automata. This is Turing machine is the another kind of machine, that is called linear bound automata. So, this cannot be accepted by the context sensitive language, cannot be accepted by the push down automata. For this we can have 2 stack. For this, if this language is given, we can use here 2 stack, 2 separate stack you have to use. What you have to do here, we have to take here 2 stack, stack 1 and stack 2. Using these 2 stack we can stack 2, for using these 2 stack we can design this language, and this 2 stack you can say this is in Turing machine. If you will take single stack, that is in PDA, and you can use here 2 stack, and that will be declare as a Turing machine. So, next see here. So, computable language, if the string is the language, then machine should be accepted. See, what is the computable language? This computable language means this Turing machine we can have decidable language, another is undecidable language. If the string is in the whatever input, suppose we have taken a diagram, DFA diagram, you see here one DFA diagram is there. Suppose we have taken here A, and this is final state, this is Q0 and Q1, and here all the at least one will be there, and you see here when you will take all the input, suppose A is input, then A is accepted. Suppose we will A is accepted, A is accepted. Suppose we will take here B, then it is reject, it is reject, it is rejected, it is rejected. So, if the string is the language, then machine should be accepted. If string is not in the language, then machine should reject. If it is means this language is decidable, this is decidable. For each input we can decide for the each input we can decide either it is accepted and rejected. we get a solution for each and every input, either it is accepted or rejected. See this language L equal to a to the power n, b to the a to the power n, and this is a to the power n, n greater than this is n is greater than equal to 1, sorry, n greater than equal to 1, this n is greater than equal to 1. So, here is the design the finite automata, then here is all strings, suppose 2a, then here 2a will be accepted q0 to a, then q1, then q1 to a, q1, then this is the final state. 2a is accepted by this diagram. Suppose we will take any string like that b a b a, then this should be rejected. So, here q0 to a, this is q1, then q1 to b, there is no transition, then we can say this is rejected. It is rejected by this finite automata. So, it is given that for every member of this language should be accepted. If it is not a member in the language, then should be rejected. So, that is why this is the computable language. You can say this is a decidable language, this is the decidable language. You can say this is a decidable, this is a decidable language, decidable language. So, all the language, whatever regular language, context free language, context sensitive language, up to this, these are all are decidable language, means this is for every input we can decide either it is accept or reject. For each and every input it is accepted or rejected, we can decide it. So, that is why this is called decidable language. Then come to the partially decidable, another partially computable language. This partially computable language, here suppose we have given that if the string is in language, machine should be accepted. If string is not in the language, the machine should loop. This means whatever language for a given language, we have designed a algorithm or design a machine. For this, you can have sometimes we can get the result and sometimes we could not get the result. Sometimes it will give the result and sometimes it will go to the infinite loop. It will be not decide, either it is accepted or rejected. So, like this, so this is called undecidable. You can say this is called undecidable, undecidable language, undecidable language. This is called undecidable language, or you can say partially decidable. You can say partially decidable, partially decidable. So, here if the string in the language, machine should be accept, string is not in the language, it will not show that it is rejected or not. This is also called partially decidable, partially decidable. So, here Chomsky hierarchy, it is saying that it is divided by 4 parts: regular grammar, context free grammar, context sensitive grammar, and unrestricted grammar. So, regular grammar, context free grammar and context sensitive grammar all are decidable language. For this we can have all the member will be checked by either it is accepted or rejected, but for the unrestricted grammar, that is the that for that grammar whatever language will be generated, that cannot be fully decided by the machine, that will be partially decidable. So, according to that, again we divided this recursive enumerable language in 2 parts: recursive enumerable language, recursive enumerable language and recursive language, recursive language, recursive language, recursive language. So, this is For this recursive language is this unrestricted grammar. Here it will be, sometime it will give the recursive language and sometimes it will give the recursive enumerable language. This recursive language also it is decidable. This recursive language you can, this is fully decidable. This recursive is decidable. So, up to recursive language is, this is decidable, and recursive enumerable is undecidable. Undecidable. This is the recursive enumerable language. So, for this again I can say this is another diagram. So, this 4 grammar again separated by the different type of language, like that you can see. This is regular language, then DCFL, then CFL, then this is CSL, then this is recursive, and then recursive enumerable. This is the recursive enumerable. So, this regular language, again I separated this CFL to 2 part. One is deterministic context free language, another is context free language. Then after CSL, context sensitive language, then after recursive language, then after recursive enumerable language. So, this regular language we already we have regular language. For this we have finite automata. For DCFL language, deterministic context free language, already we will go to the push down automata, that is the deterministic push down automata. For DCFL we have deterministic push down automata to accept the deterministic push down automata to accept the deterministic context free language, and then after we have CFL, and you see for CFL you can say this is a non-deterministic push down automata NPDA. We will go to the PDA in next classes, and this is the non-deterministic push down automata. Then this context sensitive language, this will be accepted by the Turing linear bound automata. Then recursive language, this is accepted by the Turing machine, and which is no loop, without any loop, and recursive enumerable language is accepted by the Turing machine, and that is for some time this will give loop for the wrong string. You can say this is the undecidable language. So, up to this regular language DCFL and CFL, CSL, recursive, and for this language all are decidable. For each and every input we can say this is accept or rejected, and here and for recursive enumerable, that is the recursive enumerable, that is not undecidable. For some input it will give the result, and some input it will not give the result. So, you can say the all the algorithm, whatever you know that in algorithm P and NP, and this is the polynomial P and NP. So, this is the deterministic polynomial time, and NP is the non-deterministic polynomial time. P is the deterministic polynomial time, P is the deterministic polynomial time. And this is the non-deterministic polynomial time. So, all the language, regular language, DCFL, CFL, CSL, recursive, for this all are polynomial time, and this is the recursive enumerable is the non-deterministic polynomial time. And this is the Chomsky hierarchy, separated the grammar like this, and also the machine, all grammar have a separate language, different language, all the and also different automata to accept the language. This is the Chomsky hierarchy. So, thank you, and these are the reference book you can follow.